sort of a brief announcement. I will be linking the slides on my webpage. There is like Clay Math Institute Summer School, and then schedule, and then under schedule you can see every talk, and then there will be materials. And there is a schedule of the computational seminar there as well. All right. So today I will discuss perhaps a very general setup. Maybe I should say the following. So like half of you are graduate students, half are postdocs. It may be the case that some of the things we will be explaining in the beginning are too easy for some of you. So just bear with us because, well, it will get more interesting later on. And in any event, so if you have questions, I encourage or we encourage that you get together in the afternoons and discuss things which you want to understand better. So again, so one of the best things about school is that there are so many of you from so many different places, and so get together, get to know each other, and discuss mathematics. Okay. Anyway, Diophantine equations, in a generality, we take an equation with integral coefficients, polynomial equation. And so I already wrote f of t. I mean, f is just a polynomial in t and some variables x1 up to xn. And so I can consider this as an equation in the unknowns t, x1, xn, or sometimes I want to consider this just as a family of equations in the variables x1 to xn, parameterized by t. So in t, one is going to be an integer or something. And so here are the examples. So something like this, it's just like a family of equations, x squared plus y squared, something like this. Or maybe x cubed plus y cubed plus t the cube, and then something like this. All right. So Diophantine equations are equations, polynomial equations with integral coefficients, and we look for integral solutions. And the basic questions, of course, is when do solutions exist? So global local principle, so we can look at the completions of the integers or the rationals, and then ask whether or not existence of solutions and completions is enough to get a solution in the rationals or integers. And this will be discussed in great detail, or is already being discussed in the course of Professor Crash. And the Brownian abstraction is the only known, at this point, global abstraction to the existence of solutions. Now, we can also ask, well, if we have solutions, do we have finitely many solutions or infinitely many solutions? And if we have infinitely many, we could ask maybe solutions satisfy some further equations, and that's the risky density or not density of solutions. Or we could ask whether we can prescribe some local conditions. So we can prescribe some local conditions at finitely many places and try to match them by rational points globally. So this is sort of weak, strong approximation depending on the setup, whether or not we are working with rational points or integral points and things like this. And then on integers, we have a natural notion of absolute value, the Archimedean absolute value, and this will give rise to heights, like maximum of coordinates or something like this. And we can ask questions about heights of smallest points, or rather smallest heights of points, or we can ask, if we fix the height, how many points do we have of bounded height? And we can ask, well, what happens if we increase the height? So asymptotic distribution. So these are the basic questions of interest to us. And the first basic question, well, can we decide whether or not an equation is solvable in integers? Decide somehow, algorithmically. So that was one of the problems raised by Hilbert at the 1900 Congress in Paris in section on math education of all sections. In any event, this Hilbert's tenth problem has a negative solution. There is no algorithm to decide the solvability of the Diophantine equation in integers. So we have a family, and in fact, one can push this statement much, much further and show that, in a sense, one Diophantine equation, or the questions about solvability of one Diophantine equation, is in fact equivalent to all of formal mathematics. So here is a version. So you have a family. All right, so you have a polynomial in the variables t1, t2, and then x0 up to xn. Now, so you look at all recursively enumerable subsets of n, like, I don't know, prime numbers or some other subsets you design. And then you want to answer the question, well, when is an integer or a positive integer in one of these subsets? Okay? And in fact, it turns out that this question is equivalent to the solvability of a very concrete equation with very few variables, actually. In the paper, Matyasiewicz Robinson can work with 13 variables. Or one way to think about it, you take some formal language, like formal mathematics, so basic notions, systems of axioms, and you have your statements. So you formulate statements from basic notions via finitely many sort of conclusions. So you can enumerate all the statements. And then you can say, well, we're only interested in theorems, that is, provable statements. Okay, so that's a set. And then you can ask, well, which theorem is provable? So that would be one of these parameters. And then the probability of a theorem is sort of equivalent to the solvability of an equation like this. So one Diophantine equation sort of covering all of formal mathematics. Sort of hard to grasp, but that's how it is. So I like to draw two philosophical conclusions from this result. First of all, hopeless to look at all equations at once, simultaneously. We have to concentrate on certain subclasses of equations, and for those subclasses, perhaps we can formulate reasonable questions or prove sort of reasonable results. So that would be sort of a positive, or that would be one conclusion to draw from this theorem. And another conclusion to draw from this theorem, so we should not be surprised that in the study of Diophantine equations, we quite often have to draw from the arsenal of tools in, say, analysis, geometry, topology, you name it, because after all, one equation is equivalent to all of mathematics. So we may as well use mathematics, all of it, to look at Diophantine equations. Well, in any event, a conjecture formulated in this paper is that you can pick n to be less equal than 3. So very few variables will suffice to deal with all of mathematics. Now, you could also ask what happens over other rings. I mean, we can look at equations with coefficients in other rings, not just the integers. We could look at fields, for example, finite fields, p-adics, reals, complex numbers. Or we could invert a few primes and look at rational numbers with denominators in this bounded sets of primes, and then see what happens. And a priori, you would get the impression that, I mean, logic, that's very far from algebra, number theory. It must be some formal deductions back and forth, but it's actually, in its modern version, also quite geometrical. And sort of most of the progress has in fact, been achieved by looking at very concrete, well, algebraic geometric objects like elliptic curves over different rings and fields. So here are some results, like very much so Bohnen and Schlappentoch proved that, in fact, you can invert, well, almost all primes. Well, you can invert primes set of density 1. It is, of course, unknown whether or not you have an algorithm to decide solvability of equations with rational coefficients in rationals. So that's one of the central problems in this field so far. It is unknown whether you can generalize the theorem to other rings of integers and number fields K. Some fields K can be handled, but not all. Well, and since we don't know how to deal with Q, we also don't know how to deal with other number fields. It is unknown whether you can get an algorithm over the C of t, function field in one variable. But there are results for function fields in several variables. And in fact, we have specialists here among us. So Christian Eisenträger, maybe she could have like a short seminar discussing. Yes? Can you explain the difference what is S equal to the set of all primes versus Q? So, well, so I can't explain the proof, but I can explain the statement. Well, so the natural question would be, if you work with rational numbers, right, can you get solvability? I mean, can you get an algorithm deciding the solvability over the rationals? So this is unknown. But you could ask, well, maybe if you look at rings between the integers and the rationals and ask the same question. And so one way is to look at rings where you invert sort of some primes. So you look at rational numbers with denominators in a finite set of primes or an infinite set of primes. So, well, in this particular result, you actually invert infinitely many primes, but not all. And if you could invert all primes, then you would have the rationals. And you invert a set of density 1. A specific set, where S is a specific set, well, I guess, I mean, yeah. Not any set, yeah. Then so the question is general Diophantine equations. So far, I mean, we're not even talking about hypersurfaces, so okay. But there is, of course, a way if you have several equations, so you can reduce it to 1 by looking at like sum of squares of those equations, things like this, equals 0. And then having the vanishing for several equations simultaneously will be rephrased for sort of the vanishing of the sum of squares. Okay? So reducing to one equation is not a problem. Yeah?
The parameter is always runs in natural numbers.
Please, sorry?
The parameter t runs always from natural numbers.
So in the beginning we had a parameter, but now we are asking, so all equations, all Diophantine equations with coefficients in a ring. Okay? Is there an algorithm to decide that any given equation with coefficients in a ring is solvable? Okay? So, and the original question was for the ring of integers, Z, and then you could ask, well, if we look at more general rings, is it easier? Is it more difficult? And so it's actually quite an active field, and there are some recent results to that. All right, so now that we've discussed the impossibility of deciding existence of solutions, we could also ask, well, is there any way of telling whether or not we have infinitely many solutions? Okay? I mean, existence would just yes or no, and here, yes and many. And in fact, so in 93, so quite a few years after the original result, Shaitin proved a theorem that there is no such thing. You can't decide whether or not equations have infinitely many solutions. Now, the abstract is also quite telling. One normally thinks that everything that is true for a reason. I found mathematical truths that are true for no reason at all. These mathematical truths are beyond the power of mathematical reasoning because they're accidental and random. Using software written in Mathematica that runs on, well, a computer, I constructed a perverse 200-page algebraic equation with a parameter t and, well, 17,000 unknowns. And for each whole value of the parameter t, we ask whether this equation has a finite or an infinite number of whole number solutions. The answers escape the power of mathematical reason because they are completely random and accidental. All right. Doesn't look like a precise mathematical statement, but that's how it is. So what's the setup? So we have some basic rings we're interested in, and of course there's a whole zoo of rings, as we have seen, but of interest are, well, finite fields, the ring of integer z, or just the ring c of t. And our basic geometric objects we start out with are, well, the affine space or the projective space, affine space minus 0 divided by Gn, multiplicative group. So then we have varieties. We could look at equations, well, sort of non-homogeneous equations, just polynomial equations with coefficients in our ring. Or we can look at homogeneous polynomial equations, and then we could look at points, solutions with values in our ring. And why do we like projective geometry better than affine geometry? I guess they discovered that in the Middle Ages. I mean, you have these parallel lines, and it's better if they meet. And so it's easier in geometry to first focus on projective varieties. And this is what we will do first. But we will also discuss integral points and in the last lecture. So from now on, we will work projectively. And hypersurfaces are sort of the first non-trivial varieties. You pick one equation and you look, well, what happens. So hypersurface in Pn, so homogeneous equations with coefficients in some ring. And as I said, the basic rings are, well, Fq, Q, and finite field. So the basic theorems are if, well, the degree of our polynomial is less equal than n, or strictly less than n plus 1, the number of variables, then we always have a point, a rational point, and this can be generalized, in fact, to Fano varieties. We'll discuss this notion later on, and rationally connected varieties. So you can show that for a certain class of varieties, which are in a sense generalizations of hypersurfaces of low degree, you always have points over a finite field. So let me sketch the proof. I mean, the proof is, of course, in every textbook on the first couple of pages, for example, in Borevich-Shafarevich. So it starts with a delta function. And I'm told by analytic number series that the most difficult thing, or one of the difficult things to learn early on, is the many ways to write a delta function. So you have to have like a huge arsenal of ways to express a delta function. And then you sort of analyze what will work. So here you have some kind of a delta function. Well, if t happens to be p minus 1, then you're summing 1s from 1 to p minus 1, and it's congruent to minus 1 mod p. And otherwise, you sort of get 0. Now, you write, consider this equation, say with integral coefficients, and n plus 1 variables, and with such bounds on a degree. Then you show that the sum over all x's, so from 1 to p minus 1, is 0 mod p. So how do we do it? Well, this is the equation with coefficients in the integer. We just do it for monomials. So we have some monomial, so d1, dn, so they are fixed, and we are summing over all the x's. And you write it as a product, and then the sum of the degrees is going to be less than this. And then you see that for one of those indices, you have to be in this range, and in this range, you can't have p minus 1 dividing the dj, and so you get 0, and you can apply step 1. One of the sums is 0. Okay. And now you want an expression for a counting function, so the number of solutions in x0, xn of this polynomial equation. And the statement is that whatever it is, it's 0 mod p. So how do we get it? So we look at this particular equation, 1 minus f of p to the p minus 1. And again, it's sort of a delta function. If f of x is 0, then 1 minus 0 gives you 1. And if f of x is non-zero mod p, so to the power p minus 1, it's 1. And 1 minus 1 is 0. So if you sum over all the x's possible of this, then you get exactly the number of solutions. And all right, and then you take some homogeneous equation, and it has a trivial solution. Or maybe I shouldn't have written here plus 1 or something, but you have one solution, namely 0, 0, 0, 0 will be a solution of a homogeneous equation no matter what. It's not a point, because projective on Pn, this is the one thing we want to exclude, 0, 0, 0, 0. But so far, we've just dealt with equations. Homogeneous, non-homogeneous doesn't matter. And all right, so we have 1, and the whole thing has to be divisible mod p, so we have more. And so then you just find that, maybe I should have put p here, that you have at least 1 point. All right. Over Q. So what happens over Q? One of the theorems, of course, so it goes back to, in fact, Waring's problem, which we had briefly mentioned yesterday, representations of integers as sums of powers, and maybe you know it. So for any d, there is a certain number, n, so that n of d, so that if n is bigger than n of d, then the sum over j from 1 to n of xj to the d equals m is solvable for all m, say, large enough, for example. Like every number sum of 4 squares or something like this. Now, if you look at more general equations, rather than say, diagonal equations, like in Waring's problem, and now we are also going to look at homogeneous equations, then again the result is that if the number of variables is big enough compared to the degree of the equation, then, well, we can't say that we have a solution, because you can also you can always write down the sum of squares, sum of xi squares with many, many xi's, and the only solution will be 0, 0, 0 over the rationals. And you can arrange for similar things over the p-adics. But then the statement is that assuming existence of local solutions, assuming existence of points on all completions, you get a rational point. So that's the Hasse principle. And so there is some estimate here. It's not the best possible. You can get much better bounds for small degrees. So I think the best in degree 3 is P9. So a cubic hypersurface smooth, say, in P9 will satisfy the Hasse principle. That's the result of Hooley. You can do better for certain intersections of, say, 2 quadrics and things like this. But in fact, in this version, if the number of variables is large enough, you can prove not only existence of solutions, well, providing you have local points, but also asymptotic formulas, and also the thing we call weak approximation, that is, you can prescribe local conditions at finitely many points. The theorem I mentioned for cubic hypersurfaces in P9, by the way, doesn't give an asymptotic formula. It only proves the Hasse principle. But in P10, previous work by Brown, you get an asymptotic formula, things like this. Yeah? So for cubic hypersurfaces over general number fields, I think a result of Skinner covers surfaces in 13 variables, so in P12, hypersurfaces in P12. All right. And in some more recent approaches, one also studies FQ of t, or the corresponding field. So, well, how does it work? Why do we assume existence of solutions in low degrees? So we look at some, say, homogeneous equation of this given degree, and our variables are allowed to move from, say, minus b to b. Okay, when the variables move from minus b to b, the equation has degree d, so each term, each monomial, is at most b to the degree, b to the d. So we have finitely many monomials, so the range of the absolute value of f of x will be on the order of b to the degree. Now we're going to work probabilistically. So we look at f of x, and we look at f of x plus 1. Well, it's not homogeneous, but all right, it's still an equation. Or f of x plus 2, f of x plus 3. And they all look the same to us from far away. And so we would say, okay, the probability that f of x is 0 should be the same as the probability of f x being 1, or 2, or 3. Well, if that's the case, then the range of values is on the order of b to the degree, and hitting 0 should then have the probability of b to the minus degree. And how many events do we have? So we are allowed to run from minus b to b for n plus 1 variables, so that will be on the order of b to the n plus 1 events. And number of events times the probability of one event should give us the number of solutions with bounded size. And we immediately see a certain neutrality somehow. So 3 cases naturally occurring, n plus 1 minus d positive. Then as b grows, then our expectation is growing. So we are expecting more and more solutions. If n plus 1 minus d is 0, then we don't know what's happening. Nothing's happening as b changes. And when n plus 1 minus d is less than 0, the larger b, the fewer solutions. So in the end, you would say, oh, well, maybe there are no solutions at all. So that's a thing that's coming out from this rather naive or a priori naive analysis. And the hope is that this analysis is actually reasonable and provable if the corresponding statement is provable if n plus 1 minus d is much bigger than 0. And the previous theorem by Birch, well, that's what it says. If n is much bigger than the degree, in fact 2 to the degree, yeah, rather than just the degree, and then there is some constant like this, then indeed the heuristic is correct. And again, so I want to sketch very briefly the approach to this, the analytic approach. We'll have a short course on the circle method next week. You start with a delta function. So you have a polynomial f with integral coefficients. So then you want to integrate this. So you integrate this. Well, if f of x is 0, well, you have 0, you integrate 1 from 0 to 1, so you get 1. So that's okay. And if it's non-zero, well, then you integrate, and then from here to there, e2 pi I, then you really use that f of x is an integer. So we are looking for integral solutions. So x is, well, say x1, x2, or x0, xn are all integers, and f has integral coefficients. So you have integers, so you have a complete period, so you get a 0. All right. Now we want to count all the x's in, say, z to the n plus 1. F of x is 0 of size bounded, and then you write the sum over all the x's of this delta function. So it's a finite sum, so we interchange. So integral from here to there of this. And then we have a function of alpha. So alpha is so sort of our real variable here. And the question is, well, how do such exponential sums behave? Well, if alpha is 0, then we are just summing once. Okay? So, but if alpha is like 1/2, then every time f of x is divisible by 2, we're going to get 1. So we're going to get quite a contribution from all the x's with the property that f of x is divisible by 2. And 3 the same. So, but now you notice what's going to happen. When alpha is, say, equal to a rational number with a small denominator, say 2, 3, and so on, and f of x happen to be divisible by that corresponding number, then we get a contribution. But as the denominator begins to grow, f of x would have to be divisible sort of by a larger and larger number, but the x's are somehow bounded. So it's not so easy to be divisible by large numbers when you are in this box. And so this is what's kind of fundamental battle that's happening in the circle method. So you're integrating a function from 0 to 1, and you know that the function is sort of large when that alpha is, say, equal or close to rational numbers with small denominators. So the function s of alpha is quite oscillating. I've asked my colleagues to plot it. All right, so what do we see? So white noise. I mean, maybe in here I see a few points here and somewhere here, which would correspond to sort of large values, correspond to alphas, rational numbers with small denominators. So here is the x running, say, from 0 to whatever, 10,000, and then we see what happens. But most of the time, and that's sort of the property of sort of rational numbers, real numbers, Diophantine approximation, how do you approximate with alphas with small denominators? And what was the plot? That's a function s of alpha, which is the sum over all x's, say in like one parameter, x, just x, from 1 to b, where b is 10,000, e to pi I, alpha f of x, and I go over alpha. So it's rather widely oscillating. Sorry?
I mean, it's a complex function.
Well, yes. So I'm taking the absolute value of that, and then I want to see, how large is it. And the claim was that if alpha is sort of close to or is equal to a rational number with small denominator, then this is what you get. Yes, I should have written absolute value of alpha. Thank you. So, and now you need to formalize that. So what's the formalization? You look at major arcs, which are neighborhoods of alphas with small denominators. Well, you don't know what small means. Q here is not power of a prime number. It's just an integer. And you bound it somehow in dependency, depending on B. So you pick some real number delta. You don't know what it is yet. And in the implementation, you actually take the interval to be less than b to the minus d, which is the degree of the polynomial, minus a little bit more, minus delta. It's a positive delta. So this is like one little neighborhood of a over q. And then you just take the union of results. They're called major arcs, so you could think, well, major arcs, they fill the interval 0, 1, but in fact, they don't. I mean, their proportion, the measure of that is sort of small and gets smaller and smaller as b increases. And then you take the minor arcs, that's a complement, and then you just look at one integral and another, and then you try to bound sort of the absolute value of that, to put it into the error term, or they say in number theory, like under the carpet somehow. And then the integral of the major arcs should converge to what? Well, to what we expect, b to the n minus d, if we have n variables, and otherwise n plus 1 minus d, I mean, n plus 1 minus d, as b goes to infinity. And then there's going to be a product of local densities, so over all primes and at infinity. And you would have an asymptotic formula with this, the dominant term, provided the local densities are positive, the Euler product converges, and you can prove that this is the case once you have a local solution. So what's the main analytic input into this method? I mean, of course, there are many steps which I'm not explaining. They will come later on. The main thing is this estimate for this kind of exponential sum. So s of alpha, remember, was f of x, and then a summation over several variables. But in case of diagonal equations, and anyway, sort of like a basic estimate has to be derived for this kind of sum. It's like one variable x to the d. And that's what Weil did, thinking about problems in physics, and that's what we had mentioned. And in fact, this Weil's bound then was used in the papers of Hardy and Littlewood on this subject, and this is where everything sort of took off. So you look at alphas. So alpha is our parameter with the property that it cannot be approximated by rational numbers with small denominators, right? You know, outside this range, and what small and what large has to be, I mean, that has to be made precise, and then you derive estimates for that. And again, the details of this we'll see later on. Now, let's jump to the next ring of interest or field of interest, complex function field in one variable. So, and again, if the degree is bigger than the number of, if the degree is smaller than the number of variables n plus 1, so less equals than n, we have a solution. And what's the principle at work here? Well, so what are our variables now? So variables, okay, are polynomials in T of some degree. So that's kind of the analog of the height, so degree E. And then, so we're going to plug in this xj of t into our polynomial equation. So we're going to open all the brackets. So we're going to have a big equation in t. And we want to get 0, and so we want it to be solvable for all t. So all the coefficients somehow have to disappear. So what do we get? We get a system of e times degree plus some constant equations in t. So I'm just looking at all the powers of t. And these fj's, they're also in my function field. So let's say they're also polynomials in t. So, and we take like the maximal degree of those, and that will be in this constant. And otherwise, well, so this is a multi-index. I get e times the degree plus constant equations. And how many variables do I get? Well, for each x0 up to xn, so I get sort of e variables. The system will be solvable when the degree is small. That's it, just parameter counting. So that's the principle or function field in one variable. All right, the summary. Now, we look at solutions of homogeneous polynomial equations over some fields. So we get rational points and corresponding projective varieties. And what we do in arithmetic geometry, we study the structure of the set of those points. So from all these points of view, existence, so do we have points, infinitely many points, and maybe those points satisfy some additional properties, some density in topology, in real analytic topology. So whatever we have at our disposal. Now, on the one hand, we have sort of the algebraic complexity of the equations, degree, what we've seen before, number of variables. On the other hand, we also have the properties of the rings we put in, finite field, rational numbers, complex function field, or the real numbers. And so we are studying the interplay between the geometric and algebraic complexity of X reflected in, say, some invariants which from of the equations which we think of sort of independent of the original, of the ground ring or field, and then the structure of the field or ring we put in, so the topology analytic structure. So this is the picture we have. So this is these are our basic rings and fields. So FQ, the rationals, which we sometimes think embedded into just the algebraic closure, but sometimes we want to think them as subsets of the complex numbers, like that analytic estimate we had, e2 pi I alpha. I mean, clearly we wanted to have our integers. And then complex function field. So then we look at kind of geometric invariants, geometric classifications. So what happens? So curves, surfaces, higher dimensions. We could structure our approach based on sort of that degree of complexity. And then the thing which comes out of our heuristic is, well, should we look at equations in like many variables of small degrees? So that will be sort of the Fano case. Should we look at equations of high degree in few variables? So n plus 1 minus d negative. That would be the case of varieties of general type. Or should we look at sort of the intermediate cases and see what happens? So that's a picture. And what we'll do in this course, we'll focus on varieties defined over the rationals, so with many rational points. It's not straightforward sort of to ensure this property. Just having n plus 1 minus d bigger 0 is not good enough. We don't know whether in all such cases rational points are, say, risky dense, or there are infinitely many of those. Well, the easiest class of varieties, of course, would be just take a projective space and do something to it, like blow-ups, like P2, blow-ups of P2. Or we could look at hypersurfaces of very low degree and then rely on either the circle method or on some geometric manipulations when n is very, very large. And so our goal is to study relationships between the geometry of the variety over the complex numbers and the distribution of rational points with respect to heights, that's maximum coordinates. And other courses in the school will look at, as I said, other fields. So the whole last week, the fourth week, almost exclusively will be devoted to positive characteristic, finite fields, and the special effects happening sort of in positive characteristic. We will have lecture courses on arithmetic and geometry over C of T, Professor Starr. We will have a lecture on the classification of algebraic varieties and implications for arithmetic questions by Professor Abramovich. All right, let's focus on our task. So heights, you can either work sort of in the affine setup, and then it's just maximum coordinates. In a projective setup, so we don't want 0, and we look at rational points. So we pick representative for the GM orbit. We look at x0, xn integers without greatest common divisor, and then we have to identify. So we have still the action of plus minus 1. And so there is just exactly one representative of this shape and of a rational point, and then the corresponding height is just, for example, the maximum of the coordinates. So we get induced heights on any subvariety, affine subvariety in AN, or the projective subvariety, and again, Z and Q in the projective case. And we also allow equivalent norms. So we may replace maximum coordinates by square root sum of squares or anything else comparable to this. We have a counting function. So we have a subvariety in Pn. We look at all rational points of bounded height. And the question is, what about these asymptotics as b goes to infinity? Now, there are several questions one could ask. We could look at one subvariety in Pn and try to get very precise results about asymptotic formulas or sort of upper bounds. Or we could look, just as before, at the family of subvarieties in Pn, say x of t, and then we could ask, well, if we fix b, what can be said about nxb as we vary x, as we change the value of the parameter? So that would be sort of a question about uniform upper bounds, uniform in, say, just the degree of x, or in something else, or we could ask for asymptotic formulas. And then, of course, you want to have some geometric interpretation, because geometry is in the back of our heads all the time. The simplest case is a projective space in Pn. So we look at x0, xn minus b to b. It's b to the n plus 1, so that's b to the n plus 1. And then the choice of the height at infinity, square root sum of squares, or maximum coordinates, will give us sort of an infinite density. But then we are also insisting on coprimality conditions. So we want no prime to divide all the variables, all the coordinates x0 up to xn. So the probability of a prime dividing all of that is 1 over p to the n plus 1. the probability of not dividing z is 1 minus z, and the product of all primes 1 minus 1 over p to the n plus 1 is exactly 1 over the value of the Riemann zeta function n plus 1. So this is what happens. Now, so this is kind of in the standard setup, but thinking geometrically, we also have to account for the possibility of re-embeddings of projective spaces and other projective spaces by means of, say, forms of some fixed degrees, the Veronese re-embeddings. So you can take P1 with standard coordinates and put it into P2 with these coordinates. And then you have like y0 times y2 is equal to y1 squared. So you have a different equation, but it's still P1. And the height asymptotics will depend on these embeddings. In the standard embedding on P1, you would have b squared points. In this embedding, you would have b to the 1 points. And in general, if you look at a rational curve of a degree d in some projective space, the asymptotic will be b to the 2 over d. As soon as we pose this question about uniform bounds or bounds and asymptotics and start to look at this from all these different sides, we see some special effects happening. So one of the special effects is that I said you can have local abstractions. So there is no solution to such equation, even though it's a low degree and you can write as many variables as you like. Or there are actually counterexamples to the local global principle, and here's one of them, a cubic surface. And more examples are, will be discussed or are being discussed in course by Professor Crash. So this is one thing we'll have to certainly accommodate in our global picture later on. We could have too many points. So here we have a surface in P3 of degree 3. So 4 variables degree 3, the heuristic would say 4 minus 3 b to the 1 rational points. But we have obvious solutions. X0 is equal to minus x1, x2 equals to minus x3. So there are b squared of those. Those are the lines, the q rational lines on this cubic surface. And, well, you've learned yesterday, 27 lines. And if all those lines are defined over q, then you get 27 contributions with b squared points on each of those lines. Of course, the exact constant will depend on the position of the line in front of this b squared. But too many to accommodate our heuristic. And, well, then you ask, can you prove that there are fewer things on the complement? So the conjecture would be b to the 1 and then some epsilon, which we'll discuss later on. The best you can do for this particular cubic is 4 over 3 plus epsilon. It's a result of Heath-Brown. And then there are other effects we'll have to accommodate, namely singularities. I very briefly mentioned that in Birch's method, you needed as an assumption that the hypersurface is smooth. So what happens when you allow singularities? So here we have 4 variables. The 2, 3, 4. I think there are maybe too many variables here. x1, x2, x3. Sorry. Anyway, 4 variables. Degree 4. We expect b to the 4 minus 4, b to the 0, maybe b to the epsilon solutions. But in fact, you prove that there are b to the 3 over 2 points of height less equal than b on every Zariski open subset. So you could exclude some accumulating subvarieties, and still you have too many points. So what is it? Well, it's a singularity that we'll have to analyze. So here are some upper bounds, uniform with constants depending only on the degree, dimension, and epsilon, but not on the concrete choice of a hypersurface in Pn. So that's the theorem of Pila from 95. So basically, dimension plus something, so plus is 1 over degree, plus epsilon. All right, but uniform. And remember our heuristic, it was n plus 1 minus d, where d was the degree. So if the degree is bigger than 2, then certainly better than b to the dimension, right? If you're looking at hypersurfaces, say xf and Pn, dimension, codimension 1. So there are some refinements of that. So we have, like for affine curves, you can do better. I mean, you have a uniform bound depending only on the degree of the shape, like 1 over the degree and then something. Recent result I want to mention, Ellenberg-Venkatesh, we look at rational points on curves of genus bigger or equal than 1, well, we know in curves of genus 1, there are probably log b to like r over 2 points, where r is the rank of the model Weyl group. And on points of genus bigger or equal than 2, the theorem of faulting, there are just finitely many points. So these theorems will be explained in the course of Professor Darmon next week. So there are finitely many points. So we are just trying to figure out finitely many. And here we have b to some power. And the issue is that it's very hard to get uniform bounds. For each concrete curve, there are finitely many, that you know. But as the coefficients begin to change of your equations, the bounds are getting worse and worse. And so the best uniform bound right now is 2 over the degree minus delta. So you can push these things using sophisticated fibration methods to prove so these kind of results, uniform bounds depending on degree, dimension, and epsilon, which are now dimension, well, it's still not very good here, but here it's down to dimension plus epsilon rather than dimension plus the delta, 1 over the degree for larger degrees. And finally, so that's it. So this is what I wanted to put down. And now, slight generalization of our height setup. We want to look at finite extensions of the ground field. So the analog would be product over all relations maximal coordinates. So of course, the first question, what happens for projective space? So you get some formula. Class number, regulator, number of units in the field, zeta function of the field, n plus 1, R1, R2, real complex embeddings, discriminant. So all the invariants you can think of, but b to the n plus 1 is the thing we expect and we want. So I should stress right away that the height which we are using here is not invariant under field extensions. For people working with algebraic points and proving theorems over Q-bar points, it is very essential to have the heights normalized in such a way that when you pass to a field extension, the height is still the same. But we normalize the heights differently. When we pass to a field extension here, the height becomes the height, the previous height, to the 1 over the degree of that extension. Okay? So we'll come back to this later. All right, so look at hypersurfaces in Pn. So what are the obvious open questions? We'll assume we have dimension, well, at least 3. Potential density. Do we have the risky density of rational points, at least after finite extension of our field? What about the touristic formula, which we wrote down? Can we prove b to the n plus 1 minus the degree with some constant tau in this range, n plus 1 minus d bigger than 0 and greater than 0, and again, dimension bigger or equal than 3, and smoothness is also essential. Finally, this constant, well, it should be a product of local densities, just like predicted by the circle method. So in dimension bigger or equal than 3 for hypersurfaces, so these are sort of basic expectations. Any result in this direction would be great. So what happens in low degree, in degree 2? Well, it's okay, except that when you have P3 and it P3 a quadric, that happens to be a product of P1s, P1 times P1 over the ground field, a split quadric. Well, then you get, well, with respect to the standard height, well, n plus 1 minus t, so b squared points, so 3 plus 1 minus 2, but there is a log contribution. And the log contribution comes from the rank of the Picard group being 2. So, but in degree bigger or equal than 3, this is what we would expect in higher dimensions. Cubic surfaces are a very special case. So, again, for quadrics, we have Hasse principle, we can count points, and so everything is great. But in the cubic case, it's sort of the lowest degree where things become very interesting from the arithmetic point of view. We have global abstractions, and I wrote down one of the examples previously. What about linear growth? So we don't know that, but we conjecture. So we have in P3 4 variables minus 3 b to the 1, and there will be this log contribution, r minus 1. What about the leading coefficient? Well, now the leading coefficient is not going to be a product of local densities like we've seen before for hypersurfaces in dimension equals than 3. It's a rather complicated thing, so these are the conjectures. It's a product of 3 numbers, so alpha is some rational number, which I'll introduce later on. Beta is the order of a Galois cohomology group. And again, you've probably seen it already, or will be seeing it in later this week. And tau, the Tamagawa number, it is kind of a product of local densities. It's an adelic integral over, well, there is some measure here, so a Tamagawa type measure. But you integrate not over all adelic points, but over the closure of rational points in the adels and the direct product topology. So again, we'll come back to this leading coefficient later in this course. And for a split cubic surface over Q, that is, all the 27 lines are defined over the ground field. Or in the rational image, so you take P2 and you blow up P2 in 6 Q rational points in general position. So this is what you get. Alpha is this. So beta is just 1. And tau, well, there is no, I mean, here you really integrate over the adels, and then you do get a product of local densities. And for almost all primes, you see this. So that's your local factor. What do we know? There are some lower bounds, and one of those bounds was derived by Elkis, in fact, in May at a conference in Banff. So the complement of exceptional curves, those lines, will have at least b log b r minus 1 rational points. So in fact, you can pick any Zariski open subset. It's actually for any x0, Zariski open. Yeah, so on the lines we have b squared. I give anyway, there are too many. So the issue is that for any, bands Zariski open, you have this. Now, not for all cubic surfaces, unfortunately, but at least for cubic surfaces which over F are blowups of P2. Now, the points need not be defined over F. The cycle is defined over F. The points are still conjugated. So you take some cycle in 0 cycle in P2 is 6 points with some Galois action, blow that up, and then you get this lower bound. So previously, there was work by Slater and Smith and Dyer proving similar results, similar lower bounds, provided the cubic has 2 skew lines over the rationals, and only over the rationals. Upper bounds are interesting. So the first upper bound where you were able to do better than points on those lines. I mean, 52 over 27 is less than 54 over 27, which is 2. So better than b squared. So that's due to Heath-Brown in 2002. And Sahlberger improved this to b to the square root of 3 plus epsilon recently. And for one cubic surface, a singular one, there is the expected linear growth conjecture and leading coefficient as well. So that's one particular cubic surface with a singularity of type E6. And that's due to Derentals. And there are improvements on error terms and joint work with Browning and Algebraic. And so that's a cubic that was on the poster of the Summer School. So in this case, we do understand the asymptotic of rational points of bounded height, and here are a few points of small height. All right, thank you.